Hi, hi Narmada. Okay, so let's wait a couple of minutes, then we'll start. So last week, actually, you asked for the unit conversion problem, or someone else? Okay, 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 cool. Okay, so let's start. Then I hope others will join today. Okay. Okay, so is my screen visible? Just one minute.
Yes.
Okay. Okay, so this is question number 50 and 51 from 2013 paper, and the question is the heating a mixture of ammonium chloride and sodium tetrahydroborate, which is actually sodium borohydride, NaBH4, gives okay, let me just check. Okay, so the question is the heating a mixture of ammonium chloride and the sodium borohydride gives one liquid product X along with the other products under ambient conditions. So we have to find out the compound X. What is the compound X? And the compound X is an example of like ionic liquid or molecular cage or any heterocycle. We have to find out. Okay, so in this question it is asked that it is a mixture of ammonium chloride, which is NH4Cl, and sodium tetrahydroborate, which is nothing but sodium borohydride, which is NaBH4. Sodium borohydride is a reducing agent which can donate H minus or the hydride ions. Just for information, it can donate H minus ion, and it is a reducing agent. So the mixture of NH4Cl plus sodium borohydride will give NaCl plus a compound named as boragine N3B3H6 plus H2. So this is the unbalanced reaction scheme. So the compound X will be N3B3H6, which is known as boragine. Now there are some important properties of boragine. If you write down the structure of boragine, which will look like this. So it is a heterocycle with alternative N nitrogen and the boron atom, and we know the nitrogen atom has a lone pair, and boron atom actually has empty pz orbital or empty p orbital. So the nitrogen lone pair can actually donate its electron to the empty orbital of the boron. So it can donate this electron like this. So if you write down the alternative resonance structure, it will look like this, like nitrogen, boron, nitrogen, boron. So it will be a double bond, and nitrogen will be plus because it is donating its electron, and boron atom will gain minus charge. Similarly here also and here also. So it is a heterocycle, so it is a cycle compound, and it has 6 bonds, and each bond distance, like it can form resonance structure also like benzene, and the bond distance is actually 1.44 angstrom. So but it is quite so due to the similarity with the benzene, like if you write down the benzene structure, so this is benzene, H3 if you write down. So benzene has all carbon atoms, and the sp2 hybridized carbon atom are sp2 hybridized, and each pz orbital of each 6 carbon atom will overlap with each other to form these pi clouds. So benzene also has 6-membered ring, and boragine also has 6-membered ring. So due to the similarity with the structure, boragine is also called the inorganic benzene. But benzene has all carbon atoms, so it is actually non-polar in nature. But boragine has nitrogen and boron atom, alternative nitrogen and boron atom, and we know that the nitrogen is more electronegative compared to boron. So there is an electronegativity difference between these two atoms. So that's why boragine is polar in nature, and due to its polarity and electronegativity difference, boragine is also reactive, highly reactive compared to the benzene. So these are some important properties of boragine. Now boragine also has a 6-membered ring, and it also has the 6 pi electrons. So that's why the boragine is also like quite aromatic in nature. So it has a aroma, it has a particular smell like benzene. Okay, so these are some extra information. So like now let's move forward to the question number 51. The compound X is an example of A, ionic liquid, B, saturated heterocycle, C, molecular cage, and D is unsaturated heterocycle. Now clearly it is a heterocycle compound, and but if you form this structure, we can clearly see that the nitrogen and the boron share the double bond, like so it has 6 pi electrons. So that's why it is clearly unsaturated heterocycle. Saturated heterocycle, saturated compound means all the bonds between the atoms are single bond. Single bond. Unsaturated means it has double and triple bonds. So the boragine has 6 pi electrons, and there is a double bond between the nitrogen and the boron atom. So it is clearly an unsaturated heterocycle. Okay, so for question number 15, option C is the correct answer, and for question number 51, option D is the right answer. Okay, so any doubts or questions from this question? Okay. Somebody raised an hand, I think. Okay. Okay, so let's move forward to the next question about. Just a second. Okay, so this is question number 21 from 2012 paper, and this question says, among the following donors, the one that forms the most stable adduct with the Lewis acid BCS trimethyl. So trimethyl borate is option A is 4-methylpyridine, option B is 2,6-dimethylpyridine, option C is 4-nitropyridine, and option D is 2,6-di-tertiary butylpyridine. Okay, so it is the question about Lewis acid Lewis base adduct. So we know that the boron trimethyl borate, that means now if you write down the structure, it will look like this. So boron atom is like sp2 hybridized, and boron atom has empty pz orbital. Now it has triangular structure, and the angle between these two CH3 bond, BC bond, it is 120 degree. Ideal bond angle is 120 degree, but in this case it can be little bit different because of the steric effect. Now ideal triangular bond angle is 120 degree. Now this is so the trimethyl borate actually acts as Lewis acid, so it can accept any electrons from any Lewis base. Now these four options, this 4-methylpyridine, 2,6-dimethylpyridine, 4-nitropyridine, and 2,6-ditertiary butylpyridine acts as Lewis base. So if you write down the structure of normal pyridine, which will look like this. So this is the structure of pyridine, and nitrogen atom has lone pair. So this lone pair actually participate in resonance with this ring also, like this. Also, this nitrogen atom can donate this lone pair of electron to the empty p orbital of the boron atom and forms the Lewis acid base product or adduct. So we have to find out the most stable, which of the substituted pyridine will form the most stable adduct with BCH3 Now the structure of 4-methylpyridine is like this is 1, 2, 3 and 4 position. So 4-methyl means there is a 1-methyl group here. So this is the structure of 4-methylpyridine, which is option A. Now option B is 2,6-dimethylpyridine, which is this is a 2 position and this is 6 position. So this is the 2,6-dimethylpyridine. Option C is 4-nitropyridine. And option D is 2,6-di-tertiary butylpyridine. That means tertiary butyl means this group. Yeah, for this question option A is the correct answer because okay, yeah, you are right, option A is the correct answer. Why? Can you tell me why? Yeah.
It's more stable.
Yeah, like like for pyridine to donate this electron, like CH3 group is electron donating group. We know that it has the plus I effect. So there is a CH3 group in the 4 position, at number 4 position. So that means the CH3 group can actually donate this electron. Like it has a positive inductive effect. And there is option B has the 2 CH3 group, 2 methyl group, but so it can act as a steric hindrance, so that so the nitrogen cannot donate its lone pair of electrons easily. Option C has nitro group at 4 position, but nitro group has electron withdrawing effect because so due to the presence of this double bonded oxygen, so it can withdraw electrons, so it has electron withdrawing group, so the nitrogen lone pair cannot donate this electron easily. And option D, it has bulky tertiary butyl group, so this lone pair of electron is actually caged here due to this bulky CH3 group, so that's why this lone pair donation of this electron is not possible or easy. So that's why the option A will be the correct answer. So 4-methyl pyridine will form the most stable adduct with the Lewis acid, trimethyl borate. Okay, so let's move forward to the next question. Okay, here this is actually question number 25 from 2012 paper, the order of polarity NH3, NF3 and BF3. So you have to find out the correct order of the polarity of these 3 compounds. So so first option is NH3 less than NF3 less than BF3. That means the BF3 is most polar. Option B says the NH3 is the most polar. Option C says the BF3 NF3 is the most polar, and option D says the NH3 is most polar. So okay, so let's first draw the structure of these 3 compounds. So NH3 has tetrahedral structure, so this is the lone pair, and NF3 has also similar structure, their structure is similar, and BF3 has trigonal structure. Ideally, the bond angle between these 2 bonds, BF bonds, is 120 degree. So for NH3, okay, if you draw the dipole vector, so this is actually lone pair. So hydrogen atom is less electronegative than the nitrogen atom, we know that. So for this bond, the dipole vector will look like this, from positive end, positive hydrogen end, to negative nitrogen end. For this bond also, dipole vector will look like this, and for this bond, dipole vector will look like this. Then for the lone pair case, the dipole vector will look like this, because the lone pair electron has more electronegativity than the nitrogen atom, so the dipole vector will look like this. The resultant dipole vector, so it will look like this, because all the dipole vector is pointing towards the same direction, in the upward direction. So the resultant vector will be high, and it will look like this. Now let's look at the case of NF3. Now we know the fluorine is more electronegative than the nitrogen atom. So fluorine will attract electrons more towards its direction. So it will attract the NF electrons here towards this direction. So the dipole vector will point towards this direction, from positive nitrogen end to negative fluorine atom. And for this bond also the dipole vector will look like this, and for this bond also the dipole vector will look like this. And for the lone pair electrons the dipole vector will look like this. Now if you just think carefully, so for this case the dipole vector, 4 dipole vector is look like this. So if you just do the resultant of this vector, so there is because 3 dipole vector, this 3 dipole vector, the resultant of this 3 dipole vector will look like this. And okay, the resultant of this 3 dipole vector will look like this, and the dipole vector corresponding to the lone pair of electron will look like this. So these two, the resultant of these 2 dipole vector will actually look like this, but the magnitude of this dipole vector will be small compared to that of the NH3, because in the NH3 case all 3 dipole vectors point towards the same direction, so the resultant will the magnitude of the resultant dipole vector will be high. But in this case the dipole vector corresponding to the lone pair and the 3 resultant dipole vector are opposite in direction, so the magnitude of the resultant dipole vector will be small. Now let's look at the BF3 case. So boron is sp2 hybridized and it is trigonal in nature, trigonal structure, and the angle between these 2 BF bonds is ideally 120 degree. So fluorine is also more electronegative than the boron atom, so the dipole vector will look like this, and for this bond it will look like this, and for this bond it will look like this. So just for this bond and this dipole vector the resultant will look like this, and the dipole vector corresponding to this BF bond is this. So due to this trigonal structure geometry and 120 degree bond angle, ideal bond angle, so these 2 dipole vector will cancel out each other because it is actually 180 degree and opposite in direction. So the resultant, the magnitude of the resultant dipole vector will be 0. So boron difluoride will be non-polar. Okay. So boron difluoride will be non-polar in nature. So correct order of the polarity is, so first is NH3 is more polar than the NF3, then BF3, because BF3 is non-polar. So this is the correct order of polarity of these 3 compound. So the correct option will be option B. So NH3 is more polar than NF3 and BF3 is less polar or non-polar. So for question number 25 the option B will be the correct answer. Okay, so any queries from this question? Okay, great. Okay, so now actually I will be I'll be showing just some units of important quantities and the interconversion between different unit systems for some important quantities through some examples. Okay. Okay, so let's first start with the force, unit of the force. So I'll be writing just some important quantities which will be important for the chemistry gate exam. So force, the unit of force is SI, or the MK's unit is Newton, we know that, and the CGS unit is dyne. Okay, so 1 Newton, that means 10 to the power 5 dyne. Now for the dimensional analysis, we know that the force, let's call it with F, the force equal to mass times acceleration, right? M times mf, or F equal to m times m, mass times acceleration. So the SI unit of the force will be mass. SI unit of mass means kg, and acceleration is actually v upon t. So the SI unit of acceleration is meter second to the power minus 2. So the Newton will be 1 Newton means 1 kg meter second minus 2. So this is the representation of 1 Newton in SI unit. Similarly in CGS unit, if we write down 1 dyne will be equal to 1 gram centimeter second minus 2. Now from this conversion, actually you can write down the dimension of force. So dimension of force will be just dimension of kg. Kg means mass means m, then meter means L, and second is time, t minus 2. Okay, so this is actually pretty easy. And now if you just write down the unit of energy, the unit of energy and the unit of work has the same unit or same dimension. So energy, so SI unit of energy, we know that the joule, and the CGS unit of energy is actually arg. Okay, so we know that the energy and the work has the same unit and dimension. So we know work equal to force times displacement, right? Force times displacement, or F times T. So force, so if you write down the unit of energy, or W, in CGS unit, the CGS unit of force is dyne times the distance. CGS unit of distance means centimeter. So dyne centimeter equal to arg. So 1 arg equal to 1 dyne centimeter. Similarly, 1 joule will be equal to 1 Newton meter. Now you can also write down the dimension also, like force, the dimension of energy will be dimension of force, which is m L t minus 2 times L. So total m L square t to the power minus 2. Now another important quantity is actually pressure. So pressure, we know that the pressure P equal to force per unit area, right? F upon F. Pressure equal to force, amount of force per unit area. So we know the unit of force, which is CGS unit, like in CGS, gram centimeter second minus 2 times area and unit of area is the centimeter square or meter square in CGS or SI unit, so cm square. So total it will be gram cm minus 1 times second minus 2. This is the CGS unit of pressure, and similarly the SI unit will be kilogram meter inverse second minus 2. Now pressure can also be expressed by F upon m, means SI unit will be just Newton per meter square, and Newton per meter square means 1 Pascal. So actually 1 Pascal equal to 1 Newton per meter square, and which is similarly equal to 1 kg meter inverse second minus 2. Now there are various units of pressure, and like ATM, bar, millimeter of Hg. So 1 ATM, so this is important actually, 1 ATM equal to 1.013 bar. So also 1.013 into 10 to the power 5 Newton per meter square or Pascal. So 1 ATM equal to 1.013 into 10 to the power 5 Pascal, and 1 ATM is 1.013 bar, and in millimeter of Hg unit, so 1 ATM equal to 760 mmHg. So this will be needed to interconvert some of the units problems. So this is actually all about pressure, and sometimes you need to interconvert mass from the atomic mass unit to kg. Like atomic mass unit means the mass of a single atom. We know that the mass of 1 mole of any atom, 1 mole, let's say carbon atom, 1 mole of carbon atom will be 12 gram, right? So 1 mole means there are Avogadro numbers of carbon atom. So for, let's say, Avogadro number is Na, which is the mathematical amount is 6.023 times 10 to the power 23. So for Avogadro number of carbon atoms, the mass will be 12 gram, and for 1 carbon atom the mass will be 12 divided by Avogadro number of gram. So you have to just divide with the Avogadro number, which is 6.023 times 10 to the power 23, to get mass of a single atom. Now to convert it to the kg, so 1 gram equal to 10 to the power minus 3 kg. So that means 12 divided by Na times 10 to the power minus 3 kg. So basically 1 AMU, which is atomic mass unit, 1 AMU will be 1.66 or 67 times 10 to the power minus 24 kg. So this conversion will be important. Now if the mass of any atom is given in the AMU unit, which is the atomic mass unit, and you need to convert the AMU to the kg or gram unit, so 1 AMU will be 1.66 times 10 to the power minus 24 kg. And now the unit of angle, we all know that the for in the angle has different units like radian or degree like this. So we know that 360 degree equal to 2 pi radian. That means the circumference of a circle. So 2 pi radian will be equal to 360 degree and 180 degree will be pi radian. So often you need to convert the radian to degree. So we have to remember 360 degree equal to 2 pi radian. Now the most important unit is unit conversion is actually in spectroscopy. Like often in questions it is the spectroscopic signal of different bonds or different molecules is actually expressed in centimeter inverse unit. So okay, now for spectroscopy signal means actually for let's assume the molecular particular bond, let's say HF molecule, and we need HF IR spectroscopy of HF bond, HF molecule. So it is actually from 0 to 1 transition. So HF is actually let's assume the HF as Morse type oscillator, and it is 0 state, it is 1 state. So 0 to 1 transition is called the fundamental transition. So it is expressed in, let's say, centimeter inverse unit. Okay, so centimeter inverse means it is actually expressed in wave number unit. What is wave number? Wave number is expressed by nu bar, which is 1 upon lambda. Lambda is the wavelength. So 1 upon lambda is the is wave number, and we know the unit of wavelength is the unit of length, which is centimeter or meter in CGS or SI unit respectively. So the unit of wave number is centimeter inverse or meter inverse. Now to apply this spectroscopic signal in your mathematical expression, like we know the E equal to energy is equal to h nu. H is the Planck constant, which is the unit of joule second in SI unit. Planck constant as the unit of joule second. It is very important to remember. Now the value of Planck constant in SI unit is 6.626 times 10 to the power minus 34 joule second in SI unit, and here nu is the frequency. Now often just you can interconvert between these two, like E equal to nu equal to you can write C by lambda. We know frequency equal to nu C upon lambda. C is the speed of light, lambda is the wavelength, and 1 upon lambda is nu bar, so it is actually hc nu bar. So E can be also expressed as hc nu bar. Now let's look at this. C times nu bar equal to nu. So let's say nu bar has the unit of centimeter inverse, and we know the unit of frequency is second inverse, right? So if you just multiply nu bar with speed of light, that means unit of speed of light is centimeters per second times unit of nu bar is centimeter inverse, so it will cancel, and the unit of frequency will be second inverse. So to get the value of frequency nu in second inverse unit, you have to just multiply the wave number or nu bar in centimeter inverse unit times speed of the light c. So c times nu bar will be nu. You have to be careful while interconverting this. Now from centimeter, often you need to just convert centimeter inverse to electron volt unit. So 1 electron volt will be 219,474.63 centimeter inverse. You can remember that value, so it is actually important. Often we need to convert between the centimeter inverse and the electron volt. So 1 electron volt is 219,474.63 centimeter inverse. Okay, so actually most importantly, you need to just you have to be careful while solving the spectroscopic problem from the spectroscopy unit, because in that case often the amount of spectroscopic signal is expressed in centimeter inverse unit. Sometimes the angular frequency is mentioned, which angular frequency means omega. So omega is equal to 2 pi nu, that means 2 pi times frequency. Here omega is angular frequency. So you can just call nu equal to c upon lambda, so equal to 2 pi c nu bar. So we know that the h e equal to h nu, so it will be just, if you write down this, h upon 2 pi times 2 pi nu. So h upon 2 pi is called h bar. So h bar times 2 pi nu means omega, angular frequency. So E is also expressed as h bar omega or h nu. Okay, so you have to remember that. Okay, so I think that's it from my side. So if you have any particular specific question, you can ask.
So
Yeah.
sir, please explain the value of gas constant in different units.
Yeah, okay. So the universal gas constant, which is we know that we denote with R. So R in joule unit is 8.314 joule mole inverse Kelvin inverse, right? Joule mole inverse Kelvin inverse. And so you can just get the unit from this gas equation. PV equal to, we know that nRT. So for n equal to 1, that means what 1 mole, n is the number of mole. Now for n equal to 1 means 1 mole, which is equal to PV equal to RT. So R will be equal to PV upon T. So from that you can get the SI unit of R, which is for 1 mole case, that's why it is mole inverse here, and T is the Kelvin inverse here. Now PV means work, pressure, volume, work. So PV, so unit of work is joule, or in unit of energy is joule. So that's why the unit of R is joule Kelvin inverse, that's for 1 upon T, and mole inverse. Why? Because for n equal to 1 case, that means per mole. That's why it is unit is joule mole inverse Kelvin inverse, and the value is actually 8.314 joule mole inverse Kelvin inverse in SI unit, and in CGS unit it will be just 8.314 times 10 to the power 7 arg mole inverse Kelvin inverse. Now in like there are many units of R also, like ATM unit, which is actually 2 I think, I've forgotten the value. I think it is actually 2 point something 2.023 in ATM unit. ATM mole inverse Kelvin inverse, like in ATM unit. Now the importantly, often you see in the problem that sometimes it is expressed in the KB unit, or sometimes it is expressed as R. So KB is the Boltzmann constant, which is the value of 1.38 times 10 to the power minus 23 in SI unit, and 1.38 into 10 to the power minus 16 in CGS unit. So actually it is constant, and if you just multiply Avogadro number with KB, you will get R. So R equal to just Avogadro number times KB. So if you want to get KB from R, you have to just divide the R with Avogadro number. So you have to be careful where the KB is mentioned or where the R is mentioned. So to get the KB, you have to just divide the gas constant R with the 6.023 times 10 to the power 23. Okay. Now anything you can ask.
Sir, how
Yeah.
to convert joule to calorie?
Oh, okay. So joule to calorie is 1 calorie equal to 4.2 joule. So you can remember that, like 1 calorie equal to 4.2 joule. Or okay, I will just share the screen. CGS unit of energy is arg, and SI unit of energy is joule. So 1 joule equal to 10 to the power 7 arg. So that's why when you are expressed R in SI unit, it is 8.314 joule Kelvin inverse mole inverse, but in CGS unit it is 8.314 times 10 to the power 7 arg Kelvin inverse mole inverse. So 1 joule is 10 to the power 7 arg, but 1 calorie equal to 4.2 joule. When you need to convert joule to calorie or calorie to joule, you have to remember 1 calorie equal to 4.2 joule. Okay. Anything? Clear now?
Yes, sir. Thank you.
Okay, so I think in the next 2 weeks I will be just solving few more questions from 2012 paper. Then if you have any specific topics to discuss, you can ask, you can let me know, we will discuss. Okay, so let me just stop here today, and then we'll meet in the next week. Is it okay?
Yes, sir. Thank you, sir.
Okay, thanks. So see you in the next week. Thanks for joining.